Okay, we're going to now move on to actually doing some modeling in SPM directly. And so this will involve basically building some predictors like we did before with the code and fitting them to the data at every voxel in the brain. So here's the parameters we're going to need. They're in your handout. And so we've got the TR, which is 2 seconds, and then we've got these parameters which specify the timings when some events happen. So this experiment was very simple. Someone's lying in the scanner, moving a joystick. During the control condition, they just had to watch a screen with some arrows lighting up, but they didn't have to act. In the queued condition, they were queued which direction to move the joystick. So at 3 seconds, they had to move the joystick, then 103 seconds. But each time was for a block of 21 seconds. So they were moving constantly for 21, pretty constantly for 21 seconds. So these were the starts of each of those blocks. And then for the free condition, they had to choose between two arms. Okay, so let's copy and paste those, or you can just type them straight into SPM here. So once you've got this command prompt here, you can just paste things in. Okay. And then go back, and do the same thing for, actually, they're all the same, that's fine. Copy. So these variables now exist. We type in whos, it lists all the variables that exist. So actually, I'm just going to clear everything because we don't want all the other stuff that was there before. So we'll copy these again. The instruction started the first thing, and then every 24 seconds there was a new instruction, so that's why it's going like that. So yeah, so there was one other condition, which is instruction. And that's an important point. When you model data, you should try and model everything you know is happening. Collapsing conditions together or ignoring mistrials isn't a good idea. If people have mistrials, that's fine, don't include them in the main condition, but have a separate condition called missed trials, for example, or something like that. Okay, so now we have in the workspace this information. We've got the onset times, so for control, we have these points in seconds, queued and free. And then we have durations, control. And actually, in all cases, free and queued are also 21, and then instruction is 3 seconds. Okay, so we're about to model the data. So we're going to need our smooth normalized data here we've got from earlier on, which is here, SWA task. We'll also need the realignment parameters to include as nuisance regressors. And that's it. So first thing we do is, I always advise make a directory when you're going to do a new analysis, because you'll find often you'll end up doing multiple analyses of the same first each subject's data. So it's best to create a new folder each time. Okay. And now we'll get going with SPM. So if you click specify first level model, should open a window. So I didn't press it properly. Ooh. SPM seems to have had a problem. Let's do SPM fMRI just to see if it settles itself down. Check still recording. Yes. This is still recording. Yes, it is. Okay. Okay. So let's click specify first level. This will open the batch window. That's better. Now we're going to do the other steps we need to do as well, which is stats model estimation. So this will end. All this does, you'll see, is it takes the output of the previous step and runs as normal. So there's no need for us to go through that in any detail. Okay, so first thing you have to do when you specify a model is you have to specify the directory, which we've just created. So we select analysis. Then we specify the units of design, whether it's going to be in seconds or scans. I always work in seconds because With scans, if things are so, like, let's say your TR is 2 seconds and a stimulus happens at 3 seconds, well, how do you code that? It's easier to put it in terms of seconds. Your interscan interval is your TR, your repetition time, as they explain down here. So that's going to be 2. And the microtime resolution can be left for short TRs relatively unchanged, but you can equally set it to the number of slices, so in our case 38. And if you've done slice timing correction, this should be the one that's used as the reference, so in our case 2. Okay? So that's just giving the model some basic information about the data. There's 38 slices, the resolution, everything's adjusted with respect to slice 2. We're going to give all our onsets and timing information in terms of seconds, and the scan took 2 seconds to acquire. So let's create a new subject. Yeah. Okay. So interestingly, you could have multiple sessions within a single subject, and you could just basically create new sessions and stack them together. You get a bigger model. So let's pick our scans. So this part's a bit boring. All we're doing is selecting and inputting stuff, but we'll get to the interesting part in a minute. So again, we're going to select our SW files. So little hat SWA 1:300. Right click, select all. Okay, so hopefully everyone's with me so far. The next thing we need to specify the conditions. So these are our task-related explanatory variables. So for example, we have 4 of them, if memory serves. We've got 1 for the free movement, 1 for the queued movement, 1 for the control condition, and 1 for instructions. So you can see here again, we've got 4 conditions so far. We can replicate them if you want, but no need. Or if you accidentally press too many, you can delete them here. So the first one's going to be called free movement, or free. I'm just going to put free for now. Okay, and its onsets, these are the times when the blocks start, are specified here. So you could just type in 58, 128, 203. 58, 108, whatever. But I'm not going to do that. Because I copied and pasted that vector in, so remember it was, I pasted in some numbers in here like that, but pasted into the workspace. So now I should be able to just type in free. And there you go. Because the variables exist here, because I copied and pasted the vectors, the vectors straight from here, I now can just call them in SPM, and that's quite useful. Now the durations, because they're all the same length, I can just put it in once, and SPM then assumes it's the same for everybody, but otherwise you'd have to have a different duration for each condition. Let's do the same thing for queued. And again here we know we have the variable already there for us to collect. So queued, and again the duration is 21. Hopefully you're all with me so far. Then we've got control. And the onsets here are just control. And again, you can see 28 seconds in, then the next block for control is 78 seconds in, then the next block is 178 seconds in, and the duration here again is 21. The final thing is instructions. So this was 3 seconds at the start of each block. And we'll say instruction. Okay, 3 seconds at the start of each block. But we don't want to differentiate between different instructions because we don't really, people are just being told what was coming up. In this case, they're 3 seconds long. So if that's okay and everyone's got that, we'll move on. If not, pause it here until you've caught up with it. Okay, so there are 2 other options which we're not going to do for this model. The time modulation gives you an extra condition which has the same onsets, but it's where the onsets change linearly over time. So in essence, where the response goes from no response to maximum response over the task. So for example, if you had somewhere where there were in your population that weren't responding, but as you learned the task, the regions became more responsive. A time modulation would capture that change. This isn't a linear change in bold signal over time, it's a linear change in the response amplitude over time. Okay, so learning is a good example. Fatigue is another example where you might expect maybe the response to go the other way. So these regions responded to begin with, and then slowly drifted away as people became less engaged in the task. The parametric modulation, so that's fine. First order just means a linear tempo modulation. Second order will give you linear and quadratic, where it's a U shape, okay, where it starts high response, goes to low response, and then comes back up to high response. In most contexts, I think linear would be the only thing you'd use. Now, obviously, if you're doing a learning experiment where you had some measure of performance, you wouldn't necessarily want to put in explicitly just a linear change. You might want to say, well, is there any brain region that encodes the actual metrics that give rise to the performance? Okay, and in that case, you could use a parametric modulator. So the parametric modulator, you say, give it a name, and then you give a value for each onset. So again, we've got 8 blocks, so you'd have to have 8 values. And these will be the reaction time during the block or the performance or whatever on that trial. And again, there's first order expansion is linear, second order expansion is quadratic. So just like you'd have with, so for the NBAC example would be a good example. So you could take the NBAC working memory task, put all the NBAC trials together, and then put in a parametric modulator that encoded the task difficulty, so 1 back, 2 back, and 3 back. So these go 1, 2, 3, 1, 2, 3, whatever. And that would identify brain regions that respond linearly with the load. But you can also include a second order parametric modulator, which say, show me brain regions which are most responsive to condition 1 or condition 3, but less to condition 2. However, if you've got a negative beta, that would be like the inverted U in a working memory task. So it would be regions with less response for condition 1 and condition 3, but maximally responsive for condition 2. It's just to say that you can encode much more complicated models, but you can also have them not only be linearly related to those parameters, but non-linearly, like, well, quadratically related or whatever. And this, you can expand it well beyond that. So I'm going to get rid of this parameter because we don't want it for now, because it's a simple block design. So hopefully everyone's with me with that. So it's just basically you can put in tempo modulation or parametric modulation. They're basically the same idea, except the tempo modulation just assumes a change across the whole experiment, but linearly or quadratically, whereas the parametric modulator, you're actually giving an explicit parameter that you think should be related to neural activity, for example, task difficulty or whatever. Okay. Yeah, generally we orthogonalize the conditions if we put in modulators. Multiple conditions is theoretically a way to just basically create a mat file, which is a matrix file from MATLAB, that has all your condition information. You can load that straight up. In my experience, I do something like this, but I don't use their specific code. And we can return to this in the automation script and the automation lab later on. Regressors are basically extra nuisance regressors, so things that you want to control for in the model. But importantly, unlike the conditions where we specify something happened at certain points in time, regressors are with respect to the volumes. So in our case, we've got 300 volumes. We've 300 individual volumes in the data. So if we want to put a regressor in, we'd have to have 300 values. So for example, we were controlling for extra movement regressors or something like that. You could put in, but it has to have one value for every single volume in your time series. So we can delete that regressor. But we do often, as I said before, want to control for motion parameters in the model. So here, multiple regressors allows us to input a mat file or a text file that has a collection of nuisance regressors. So in our case, we're going to select our RP file. Okay. And we're pretty close to being done with this. So let me go back. Okay. So one of the things about bold, as I said before, it's non-quantitative, and one of the problems is it's not stable in time. So typically, the bold signal would look like this. So it'll drift slowly over time. This is low frequency drift in the data. But our model generally doesn't have this low frequency component in it. It generally assumes the response is stable over time. So we need to find a way to correct for this low frequency drift, and what we tend to do is what's called a high pass filter. So we take a high pass filter, it filters out everything low and allows the high frequency information to stay in the data. And what you see is if you apply a high pass filter, now your data fits the model much better. Okay. So it removes low frequency information. The standard default option is 128 seconds. So that's basically a signal that goes through a full cycle. So full cycle of response over 2 minutes. And anything slower than that is removed. Typically, the filter should be about twice the size of any period of your experiment that's of interest. So if you've got a block that goes on for 30 seconds, off for 30 seconds, okay, it's got a cycle of 60 seconds. So it's 60 seconds between the start of a condition and the next time that condition starts. So the optimal filter of that would be set to 128 seconds. However, you have a problem with more complicated designs with 3 or 4 conditions, that often some parts, and you'll see with this experiment, this task, sometimes there's a bigger gap between the repetition of a trial and the next time it appears, or block, and the next time it happens. And of course, you could adjust your high pass filter further, but at some point, you stop controlling for low frequency drift by doing that. So although, okay, you leave the power to detect the response intact, you're actually damaging the rest of the model fits because the high frequency information, the low frequency information is left in the data. So we'll see that. So typically, the default option is 128 seconds. So we'll leave it at that, but you'll see what the impact of that is later on. For factorial designs where you've got like a 2x2 design at the first level, SPM can create contrast direct initially for you to take to the group level, but that's not really applicable in this case. Okay, so as we said, the canonical HRF is a standard hemodynamic response function, and we'll leave it at that because this is a block design. So the temporal variation, even with someone's on medication or whatever, that even if affecting the hemodynamic response, the block fits will probably be pretty good. So the temporal the dispersion derivative and temporal derivative will give you a little bit of leeway, but you're not talking about much more than a second, or maybe a second either way. So for event-related designs, it can have a big impact, or mini blocks even, but for reasonable size blocks like 21 seconds, 30 seconds, the variation in response, the flexibility you get from the multiple basis sets is considerably lower than you'd actually benefit from. So we'll leave this, but you can just turn on the derivatives. There are other basis sets, so finite impulse response functions, things like that. These are all progressively more flexible, so you get many more columns in the design matrix. The finite impulse response function puts no constraint on the shape of the response, and so you get a very good fit, but it's very, very noisy, and you run the risk of overfitting the data. Okay, this is used for convolving with the basis sets. That's fine. It just means if you use the derivatives, they get basically convolved in the correct way. Global normalization is a relic from the old days of PET, and I think it was taken into fMRI very early in the kind of mid-90s, but it was later decided it wasn't appropriate, so we don't use it at all. So you can just leave that as default. The masking threshold is the threshold for defining voxels within the image, and it's 0.8 means it's set basically to any voxels less than 0.8%. Having less than 80% signal where the value is less than 80% of the global of that image is filtered out. So basically, it just trims away the edges in the brain. Okay. You can explicitly put in a mask. So this masking threshold creates what's called an implicit mask. So it creates a mask of all the voxels that are going to be kept in the analysis. So any ones where the signal is less than 80% of the global are removed. The explicit mask, so let's say you want to constrain the analysis to the amygdala, for example. You could put in a mask here and only estimate the values for the responses in the amygdala. That said, you can apply a mask later on, so there's not much point in not fitting it to the whole brain. The final issue is this one of autocorrelation. And basically, one of the problems and one of the assumptions in the analysis is that the error terms, if I can go to my slides, so I've gone too far. I think I've got something in this. come back to the high pass filter, autocorrelation, yeah. So basically, one assumption is of model fitting is that the error is independent from one point in time to the next. But actually, we're sampling the same brain over time. They're doing some experiment. There's actually a lot of correlated information within the errors. So if the data fits really well, at one point it's likely to fit well in the other points, so the residual will be low. But if it basically is very poor fit on one volume, it's likely to be a poor fit on the rest of the volumes too, because basically means the response there isn't characteristic of the predictor. So the problem with it is we get this kind of correlation within the data, and we need to correct that because the correlated error gives us a boosted statistical significance. Okay, so basically it's a violation of what's called the IID assumptions. The IID assumptions are that the error is independent and identically distributed. So it's the error on one volume is independent of one on the next volume, and equally that they're independently distributed means they're not correlated with each other. They're basically randomly distributed. Okay, and those assumptions are violated and mean that the normal procedures for estimating parameters, which is ordinary least squares, isn't really valid. So what we do in SPM is we try and estimate the amount of autocorrelation in the data, and then we pre-whiten by injecting in noise basically to overcome that. Now, there has been some debate about autocorrelation correction in SPM. I'm going to stick with AR1 for now, but they've now included recently this version which comes from FSL, which overcomes some of the issues. For now, we'll just leave it as AR1. SPM select, and you can look into that more if you want. Pick the fMRI. So we click a dependency. So this is going to create the model specification, build the model, and then we're going to then estimate the parameters by feeding it in here. So we can save this. We'll save it inside the analysis folder as our model batch. And then I'm going to press play, and we will take it, and I'll come back once it's finished. Okay, so hopefully this is working again. I'm just being overly cautious because the number of times this display is switched off or the mic stopped working, but it looks like it's okay. All right, so now that model estimation is done, it's gone through these processes. It's basically estimating the model. You'll see model estimation done. We can get on basically. So non-sphericity refers to this issue of the data not being independent from one point to the next. So this non-independence of the error. But that's basically been corrected. So, okay. So once you've done this, we need to look at the results. But before we do that, I want to just quickly show you how you check whether your design, what your design looks like and how it works. So SPM probably, yeah, this sort of design matrix. So the first thing here is these are our 4 conditions here. So free movement, you can see it listed here by basis set 1, sestosync canonical HRF, queued motion, control condition, and the instruction. Okay, so you can see, and hopefully you remember when we built the code, this is just like the normal data where the responses change over time, but we're looking from above. Then we have 6 regressors here that are our motion parameters. So this is translations, so moving in the x-axis, so left and right, the y-axis, forward and back, and the z-axis, up and down, and then rotation around the x, y, and z axis. So pitch, which is rotation around x, roll, which is rotation around y, and yaw, which is rotation around z, and then our intercept. Now, an important point is to check this part here. Anything that's grey suggests that that condition isn't uniquely specified. What that means is that that condition is equal to some other condition, or to the linear sum of those conditions. So for example, if you had one condition and then you'd also the same onsets and durations being used for 2 separate conditions but split apart, then if you added those 2 conditions together, it would equal this one, and then you'll get basically lots of grey bars here. For the models fitting to work, each condition needs to be independent of each other condition. If there's basically the same point of time, if the same regressor is basically anywhere else in the model, it doesn't know where to put the signal, and sort of basically can't find any. There's basically an infinite number of solutions because it can put like a tenth of it here and 90% of it here, or it can be 20% here and 80% here, or anything in between, and it will always be a model that fits the data. So basically you get this thing saying it's not uniquely specified, or you also hear the phrase rank deficient, or not uniquely specified, rank deficiency are the kind of most common. There's one other term, but I can't remember right now off the top of my head. Okay, so we want to have a quick review of this design matrix, just check how some of these parameters. So you click on review, go into your analysis folder, and pick the spm.mat. This is the model. And we click here. Okay, so this is the model we've seen already. But if you now click on design, you can click on orthogonality. So this shows us how correlated each of the columns is. So obviously each column is perfectly correlated with itself. So dark indicates correlated. And what we see is this first free condition isn't that correlated with everything, although there's a little bit of correlation with instruction, but that's not that surprising because obviously the instruction is always at the start of the block. So you see the instruction is kind of lightly correlated with all three of these conditions. Okay, so that makes sense. However, what's more interesting is about motion. So these parameters from here are motion. So motion parameters are correlated quite a lot with each other, and that's not surprising because obviously, as I said before, your head's attached to your neck. So if you move to the left, you also roll your head a little bit. And also people rarely do pure translation in one axis. We tend to move our heads, a bit forward and to the left or whatever. Now, the other thing to remember, there's a little bit of correlation with motion here with the second condition, which is cued movement. Not terribly high, but it's worth bearing in mind that there's probably a little bit of motion confound in that condition. Okay, so that's worth bearing in mind. So it's one of the things you sometimes want to bear in mind or check whether somebody's got some kind of task related motion. So you can see here on these blocks there tends to be some motion happening when this condition is happening. Okay, so not so much at that point, but here the motion seems to be a little bit correlated with this condition, particularly in this axis here. You can see it. Not only there, but particularly. So that's probably this condition here. Yeah, it is. So you can see here, this regressor here, if you look at these periods of where there's a lot of motion, they marry up quite well with this. Actually, it seems to be this phase here that's kind of the biggest problem. Okay, the next thing to do is, so that just gives you a little idea of whether the conditions are highly correlated or there's any problems. The other thing is the high pass filter. So if you remember, we set it to 128, the default option. So anything slow or having cycle length longer than 2 minutes was filtered out. So if you click on session 1, you can plot your conditions. So here is our actual predictor. This is the free condition. And in this grey bar, this is our high pass filter. Any signal, this is in the frequency domain, so we've taken the same signal and we've now re-representing it in the frequency domain. So you can see here, there's a lot of low frequency information in this. That's not surprising. The blocks are 21 seconds and whatever. So it is a relatively low frequency experiment. But anything inside the grey box is removed. Now the key thing is the main peak of power for this condition is outside the grey box. So the free condition is probably fine. The high pass filter isn't removing isn't removing a lot of the signal, but isn't weakening our power to detect this effect. However, if we go to the cued condition, you can see one of the three peaks in there is being filtered. So we're losing, and the reason for that is because of these bigger gaps here. Big gaps. So that's a relatively low frequency. You can see there's basically these ones that are very close together. So that's probably this one, which is a higher frequency information, this first peak. Then there's some conditions that are a little bit further apart. So like here and here, they're the second peak probably. And then you have these conditions where there's periods where there's very big gap between repetition. That's the third peak, which is actually being filtered. And we can have a look at the others and just see control's fine. Again, the main peak is outside of the frequency range we're filtering. And instruction. And again, instruction frequencies are quite high, so it's not filtered. Now, obviously, if your task is if something's being filtered, okay, this just gives you some measure of the autocorrelation of the data, but it's not worth worrying about too much. You either can redesign your experiment. This is the kind of thing you have to think through. Some of this you want to avoid with your task, your experimental design. And then the other option is for this subject, do you want to adjust the high-pass filter and make it a little bit longer to bring this power back in? Now you could do that, but the consequence is, at what point do you stop controlling for the things you're interested in controlling? So you leave more noise in there, and therefore the fits get worse. So it's a balancing act. The best thing really is to pay attention when you're doing experimental design to try and avoid these sorts of artifacts. When I say artifacts, I mean effects, things being filtered out by the high-pass filter. So that's basically our model examined. Let's move inside the CD change directory into the analysis folder. And I just want to show you what's being created. So there's this file called the spm.mat, and that's basically our model file. It has all the parameters, it's got the design matrix that we plotted, it's got all the relationships between the correlation between the regressors, the covariance. It points to all these other images, it points to the data that went into the model. There's these beta images, so there's one beta for every condition in your design matrix. So in this case there's 11 betas, and if memory serves, nope, let's have a quick look at the thing. Design matrix. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's one beta, and these are the model fit parameters at every point in the brain for that. So this is, let's take beta 1. So we'll display beta 1. Oops, sorry, not beta 2, beta 1. So these are the parameter estimates at every point in the brain for the free condition. And you'd hope that in the motor cortex you'd see a response, which is roughly what we see. Okay, so the betas are higher here than they are in most of the rest of the brain. Cerebellum will also play a bit of a role as well. And let's see, the betas are highish there as well. Because people move, when they move their right hand, you see ipsilateral cerebellum, so the right cerebellum, which is what we're seeing, these higher values, and contralateral motor cortex, which is what we're seeing here. Okay, so in essence, it's fine. So you can see at every point in the brain we have an estimate of the degree to which the first predictor in the design matrix, review, fitted the data. So that the time course here explained the signal at that location in the brain over time. So hopefully that's clear. Right. Then you also have a mask image, which we can have a quick look at. And this mask is basically just I wish it would pop the graphics. So this is just basically set to 1 inside the brain, and everything outside is set to 0. And it doesn't take part in the analysis. Additionally, there's this res-ms image, which is the residual sum of squares. So it's basically the unexplained signal in the data. Okay, so that's basically the key thing. So we have a residual image, which is our, if you remember when we construct our t-statistics, they're going to be the effect size, the difference between the betas when we do a contrast, scaled with respect to the residuals. That gives us a t-score with some adjustment for degrees of freedom. So if you're concerned, go back and have a look at the code we used earlier on in this lab. Okay, so now we want to, so we've looked at the design matrix, what we next want to do is basically test some hypotheses. So we're going to test two major hypotheses. One is to identify or test if there's any brain regions which are more responsive during the motion condition, when we're doing motor condition, we're moving a joystick, than during the control condition, when we're just doing nothing. And then we also want to test whether there's any brain regions which are more active for free movement, where they're choosing, compared to the cued movement where they're told. So let's create those two contrasts to test those hypotheses. So first thing you do is you click results, and it'll ask you for the spm.mat. And you get this contrast window. Okay, so if you want to see just the T contrasts, which are obviously directional, you'll see them listed here. If you want to see F contrasts, which are bidirectional, you click here. So let's go to the T contrast. We're going to define a new contrast. So the first contrast is going to be motor, all motor. We'll say minus control rather than saying greater than control. The same thing, but sometimes people find it easier to conceptualize it as a subtraction. Okay. Actually, no, let's do it the other way around. Let's do free minus control. So we're saying 1 times the free beta minus 1 times the control beta. Does that make sense? So we're subtracting, if we take the beta for control, queued. So if we subtract the queued response from the free response and then test what's left over, if that's significant, then that's the way to test whether there's any brain regions that are more responsive to free than queued. So say 1 times the free condition minus 1 times the queued. So we're basically selecting the columns of the design matrix we want to compare. So we're saying take the free response and subtract away the queued response. Hopefully that's clear. Now, first thing it'll ask you is, do you want to apply masking? The masking will constrain the map. It doesn't change the statistics. To change the statistics, to do like an ROI-based analysis, you do small volume correction later on. So you can mask with using another contrast, which is called hierarchical contrast masking, or an image you have, or something from an atlas. In this case, we're going to say none. No. And this can ask you about multiple comparison correction. We're going to say none for the moment. We'll come back to this in a second. And it's going to ask you for a height threshold. Say leave it at default. And the extent threshold, we'll leave it default. We'll come back to that in a second. Okay, so this is a stats table we get in SPM. And I think we should have something in our stats. Okay, so contrast definition, free versus queued, and queued. So basically it's just the free beta minus the queued beta. Okay. If there's sufficient baseline conditions, so where there's basically periods where there's nothing coded, you can test it versus the baseline by just using, say, free greater than baseline with just 1. We'll come back to that in a second. Okay, so this contrast definition. This is just showing you the T-maps, the result. Okay, so let's go back here for a second. I was hoping the stats table will be explained. Oh yeah, okay, well, the stats table is listed here, basically. These are the columns, and let me go through them in SPM. Okay, so basically the stats table, the results table basically gives you a whole lot of statistical information. First, we have the coordinates for any peaks in the X, Y, and Z axis. Okay, so you can just click on these. Then we have the uncorrected p-value based on the peak level response. Now, you have to think about the images as though they're kind of like a mountain range. So you have some regions which have a very high score, like the mountain peaks, and some regions that are very low response, and so they'll have like the troughs or the valleys. And there's two ways to do multiple comparisons or to look at your images. And one is to consider only response amplitude, saying there needs to be a difference of this amplitude for me to consider it significant. An alternative approach is to say, well, look, actually, I don't necessarily think the response amplitude is going to be huge, but I think the response will be spatially extensive. There'll be a lower amplitude difference, but over a larger area, and that's what cluster level correction is. So what we have here is for each of the peaks, the peak level, we have the uncorrected p-value, the Z statistic for that peak, the t-score for that peak. We have the false discovery rate which is an approach to multiple comparisons correction where we say, I'm going to allow 5% of these voxels to be false positives. Okay? And then we have the family-wise error approach, which is slightly different, which says there's only a 5% chance that any of these are false positives. So that's the difference. Here, you're saying there will be, as far as I'm concerned, on the basis of the probability, there will be 5% of these voxels will be false positives. In the FWE, family-wise error approach, what you're saying is that there's only a 5% chance that any of them are false positives. So that's peak level correction, and you can have a look at the handout as well, which details this a bit more. And then we have cluster level correction, where we say, well, look, I don't expect the response to be that huge, but rather, you know, it might be a kind of a large-ish effect, but a small amplitude effect, but over a larger area. So a good example of this will be, for example, giving someone a drug. You don't expect that to kind of obliterate the response of a neural population, but it may modulate the effect of a network. So cluster level is quite useful for that. Also, when you compare patients and controls, for example, you don't expect response in one group and no response in the other group. You're expecting the response to be, you know, subdued somewhat or blunted a little bit in one of the groups. And again, here in cluster level, the uncorrected p-value, the size of the cluster, the extent, here in voxels, the false discovery rate on the basis of cluster extent, and the family-wise error corrected rate on the basis of cluster extent. And we're going to go through the steps for correction for multiple comparison in a minute. Set level inference basically is saying this map is significant, and it basically says the C value here is the number of clusters, and the P value is just the P value for that number of clusters. So it's saying, in this case, we're saying in the peak level, I wouldn't expect a response amplitude or a difference of this magnitude to happen by chance. In this cluster level correction, you're saying I wouldn't expect a difference of the spatial extent to happen by chance. And in this case, I wouldn't expect this many clusters to be on a map at this high threshold by chance. So these two here are based on the height threshold. This one adjusts the height threshold, so there's only a 5% chance of anything. In these cases, we pick a height threshold, and then we calculate what size cluster is required to be considered significant. In this case, we pick a height threshold, and we see how many clusters are on the map, and we say whether that's significant or not. So we're going to go through this now, and we're going to test one more contrast. So you can click results again, but in SBM12, they've boiled this thing, so you can now just click here, new contrast. And the other thing we want to do is we want to, let's say, compare all motor minus control. Now, in this case, you might think the response would be 1, 1, minus 1. Okay? And SPM will accept that. But the problem is we're summing together two betas and we're subtracting 1. So there's an imbalance there. So generally, to ensure that the analysis isn't being biased in favor of responses, because this is just a summation, we're just adding them together. We're adding 1 times this, plus 1 times this, minus 1 times this. We need to have them summing, these contrast weights summing to 0. So in that case, we say minus 2. And that ensures that the contrast isn't contributing to the effect. We're taking the average of these two, and we're subtracting away this one. So 1, 1 minus 2 is correct. Alternatively, you could do 0.5, 0.5, and minus 1. Both of those will give you the same result, although the amplitude might be slightly different, but the numbers, the statistics will be the same. So we'll say 1, 1, minus 2. Okay, press done. And we get a response here. Okay. So what you'll now see is the height threshold. It doesn't change the threshold when you've done the map. We can change it ourselves in a second. So again, here we've got the coordinates in the x, y, and z axis. We have the uncorrected p-value, the z statistic, the t statistic, the false discovery rate, corrected p-value, which we don't really care about, the family-wise error corrected p-value on the basis of peak level, the uncorrected p-value on the basis of cluster extent, the extent, or the k value, which is the number of contiguous clusters, sorry, contiguous voxels in a cluster. We have the false discovery rate, which is for a cluster, which is basically saying 5% of these clusters are bigger than they should be, and therefore false positives. And then this one here is the family-wise error-corrected cluster level correction. Now, set level is almost never used anymore, so we can ignore it. The choice really tends to be between family-wise error correction on the basis of cluster extent, or family-wise error correction on the basis of peak level. Okay. Now, what we'll do here is we'll do both types of multi-comparisons correction. Then so we'll start with peak level correction. So this is the most stringent, and what we're doing basically is we're taking the smoothness of the image. This is using mathematics developed by Euler, the expected Euler characteristic. So what it does basically says, okay, on the basis of the smoothness of this image, so how rocky the mountain range is, I can predict for any given height threshold how many peaks will come through on the map. Okay, and then I can threshold the height threshold so that there's only a 5% chance of anything coming through. Now let me just see if I have a. Oh. Right. So in essence, what we're doing here is we're basically adjusting the height threshold to leave only results that survive multi-comparisons correction on the basis of height. So we're basically there's only a 5% chance that that's a false positive. Now you can see the ones here that have a value of less than 0.05. They're the ones that will remain when we do this. So the way to do this is just to click on contrast significance level set to 0.05 family-wise error corrected. So these thresholds here are always height thresholds. So we're currently at 0.001. So we click to 0.05, and you can see now the peak FWD ones are all less than 0.05. This map is corrected for multi-comparisons. Okay? And that's it. That would be your result. You can right-click on the table here somewhere. That's being awkward. You click on these different points and it'll move to different clusters, but I'm trying to get it to, okay. Print text table, and that writes the text out here. So you can copy and paste that into like into Excel or something. So this is the same text. You just copy and paste it into Excel or something like that. You also here can jump to the global maximum, or you can just click to the top coordinate there. That's fine. And you can go to the nearest local maximum if you move the coordinate. So that's multi-comparison correction on the basis of peak, which is pretty straightforward. So you just basically go set level set to 0.05 family-wise error corrected. If you want to do cluster level corrections, let's say we're comparing groups, or we've got a drug coming in, it might be more interesting cluster corrections. So let's do that. So first thing we do is we set it back to a height threshold of an uncorrected height threshold of 0.001. Okay? And what we have to do then is we're going to use this set of columns here. So from here we go down and we find all the significant clusters. So as far as I can see, the only two that are significant are these two here. Okay? And of those, so there's basically this one here and this one here. And they have K values of 2, 4, 7, 6 and 9, 6, 0. So we take the smaller of those two values, 9, 6, 0, and that becomes our extent threshold. What we end up doing is we tell SPM at this height threshold, 0.01, remove everything smaller than 960, and all these other results go away. And so our map is corrected for multiple comparisons. So again, significance level, change. No, so we pre-adjustments, that's family-wise error correction, we'll say no. 0.001 is our height threshold, yes. In this case, we put in our K value, 960. And our map now is corrected for multiple comparisons on the basis of cluster extent. So I hope that's clear. Now, so let's say you want to look at these results overlaid onto a brain. If you click sections, overlays here, you can click slices if you want. Go to SPM. So again, we go previous, SPM, canonical. We went to this folder before. And you click T1. And you get your results overlaid like that. Well, that's okay, but it's not great. It's easier to use sections. So we click on SPM again, go into the canonical folder, and you get this, which is much easier to move around in. Okay. If you render the response, you then go to SPM and you click on Rend and you pick single subject. Style new, slightly brighten the blobs, RGB. You get a blob of that. Now, just so you know, there is an easier way to do this. I should say first, once you do a contrast, you get some new images created. You get this con image, which is just the subtraction of the betas. So con 1 here, if you remember, was the difference between beta 1 and beta 2. So it's a map where we've just subtracted these two values at every point in the brain. Con 2, if you remember, was this one plus this one minus 2 times this one. So free plus queued minus 2 times control, and the values. So that's all they are. But we get a corresponding t-scores, t-map as well, where these contrast values have been scaled with respect to the residual. And that's what you're actually seeing on the map, is the t-score. Okay? Now, there are useful tools for making prettier pictures. X-Ray View is a good one. So if you click here, you can open, you pick your SPM T-map. You can adjust your thresholds here. You can have positive and negative responses, so activations and deactivations. But you can also click here on Render, New. So I click on the render here. That's the new render, or the old render. You can get it to write out a report, and it will write out all these clusters, where the voxels are, the number of voxels in the cluster, what brain regions that cluster seems to encompass. It's not absolutely accurate, but it's a good start. So it tells you that's quite useful as well. So for that, you just click report. The other thing, so click render, you can adjust your thresholds. So here, if you set it right down, in a map like that. You can also then click slice view, and you get coronal or sagittal maps. And you can adjust, let's say 3 by 3 rather than 8 by 8. And then say increase the spacing between the slices, for example. That's not fundamental. You can also change the brain it's overlaid onto and things like that, if it's got access to them. Okay. So click on whole brain to get back the stats page. Okay, so that's our cluster corrected. The last thing you might want to do, well, it's two things. You want to save the map, so save threshold in SPM. So that will give you just this blob map, so then you can overlay it on something with thresholded. So in the view we took the SPM T map, which wasn't thresholded, and we applied, you could apply a threshold using that slider. Here you can just save out just these blobs. You could also save it out as a binary array for a mask, for example. And other than that, let's go to the global maximum. You might want to plot the response. So if you click plot, contrast errors and 90% confidence intervals, pick your condition, and that's the magnitude of the difference between the two conditions. So this was summing these two betas and subtracting this. This is the amplitude. This is of the difference. This isn't massively informative, but when we do group level analysis, plotting becomes much more interesting. The final thing really, I guess, is to do small volume correction. So let's go back. You said an uncorrected threshold. We changed this so it's got no extend threshold as well. So none, 0. Okay, so now we have an original map. But let's say I want to test a specific hypothesis that a region is responsive. So for that, I can click small volume correction. Click small volume. Now, it gives you the option to put a sphere or a box at the coordinate you were sitting at. But in our case, I'm going to take an independent image and go into my ROIs folder. So we have some images here, one for the precentral gyrus, one for the postcentral gyrus, and one for the basal ganglia. Let's put precentral. And what we can see is for small volume correction, you're spatially constraining the multiple comparisons. But in that case, it makes no sense to use cluster level statistics. You have to use peak level statistics. So you look at this column here. You can see it's kind of a binary choice because you're constraining the analysis to a region. So the answer is there an effect there or not? And in this case, you can see it's 0.010. So yes, it's less than 0.05. This suggests the precentral gyrus shows a significant difference between motor responses and the control condition. You can see it's this cluster. If you want to see what the mass looked like, I'm going to show it to you. It's just a binary mask bilaterally. Okay. So values are set to 1 inside the mask, 0 outside the mask. And it basically constrains multiple comparisons to that region. ROIs, let's go back to analysis. So if I applied contrast here, sorry, not contrast, if I apply the mask here, and I apply an image here, inclusive means use the voxels inside the mask, exclusive means use only the voxels outside the mask, so inclusive. And we'll say none for now. And these are our blobs, okay? But you can see, even though I've used the same mask, the results aren't significant. But if I click then small volume correction, image, the results now are. And that's important. So using a mask to constrain the map doesn't change the statistics. It's only when you click small volume correction you change the statistics. However, small volume correction doesn't change the map. So if you want to show a region that has a small volume effect, you may want to also constrain the map as well afterwards to produce the picture before you save it or something like that. Okay, so I think that's the key things. The handout details this again in more detail, and then we've gone through saving maps out, plots, and basic thresholding. So that's all we're going to cover for this session, and then in the next session we're going to look at group level statistics, and we'll do a lot of re-thresholding and new contrasts, and hopefully that'll be helpful.